Welcome to another episode of Transparent Physics. In this episode, we are going to continue our discussion on dynamics, specifically following up on the previous lesson introducing friction, this time showing you a sample of friction in action. Okay, so let's solve this problem out, see what we get. We'll begin with reading the question and underlining the important information. We have a 95 Newton force, moves a 30 kilogram box along a horizontal surface. The coefficient of static friction between the box and the surface is 0.32. The coefficient of kinetic friction is 0.20. Is the box accelerating? Question number one. And if so, how much? The only thing I would say, looking over the problem after I wrote it here, is a good problem, a better problem that I'm giving you here. We would specify that it's a horizontal force. We can maybe assume that's the case here, but realistically speaking, when I wrote the problem, I should have said horizontal force. All right, so we've got the information identified. Let's draw a quick sketch. So we have a reasonably horizontal surface. We have an object on that surface. And we have the forces in play. Draw a dot on the object, have all the forces coming off the dot. We have a force to the right. And since we assumed that it's going to be a horizontal force, I can just go right in and say 0 degrees. 95 newtons at 0 degrees. Going up, we have a normal force. Coming down, we have the weight. And to the right, we have a friction. Now, how long do I draw the frictional force? I don't know. I don't know if it's equal to the pull. I don't know if it's greater or less than. We'll just have to solve the problem out and find out. I will say that because it says the box is moving between the static friction and the kinetic friction, I can state that it's kinetic friction. Again, the argument there is the fact that it says the box is moving gives us a very good indication that because there's slippage, we're going to use the kinetic friction for this particular problem. So that'll streamline the solution a little bit from there. In addition, we know that the mass is equal to 30 kilograms, so we might as well just get that in there. And we'll write the mu that we're going to use. The mu is 0.20. That's going to be the handy one. And, you know, while we're at it, we're going to need it anyway, so W equals mg, the mass being 30 kilograms, and g being 9.80 meters per second squared. We can get all that together, and we see that the weight is equal to 294 newtons. We don't need it yet, but we will need it soon. Okay, and that problem is basically set up. The only other thing we should probably do before we move on is specify that our unknown is the acceleration. Now, is it accelerating in the x direction? I don't know. Well, to be honest, I do know because I solved the problem. But if this is you, you wouldn't know. And so let's just leave it as an unknown. Is there acceleration? I don't know. Let's pretend that there is and solve for it. If there is not an acceleration, it'll end up being 0. And Bob's your uncle. We don't have to worry about it. Okay, next up, we're going to set up our vector analysis table. We need room for 4 forces. Double line at the bottom. And the ingredients go on the left. And here are the recipes. Fx equals f cosine theta. Fy equals f sine theta. And we'll just throw the vectors in. We got 95 newtons at 0 degrees. We don't know the normal force. But we know it's at 90 degrees. Oh. Sorry, if I don't hold the stylus the exact perfect way, it thinks I'm pressing the button. and then it stops writing. All right, so we have the frictional force at 180 degrees. And we have the weight, which we know, so let's just plug the value in, 294 newtons at 270. When we get to this point and we want to know the values in the bottom boxes under the double line, we ask ourselves the question. The question is whether or not there's any acceleration. And as I discussed before, I don't know if there's acceleration in the x direction, so let's just pretend that there is. The math will tell us otherwise. And we know there's not going to be any acceleration in the vertical direction because it's being moved along the horizontal surface. From here, we can fill out the vector analysis table because everything sits on an axis. The math is going to be pretty quick. You can work it out on a calculator if you want to, absolutely. If it's 0 degrees, that means it's all positive x. So we can just write 95 newtons. Nothing's in the y. At 90 degrees, it's all positive y. So nothing's in the x. At 180 degrees, one thing to note here is that Fk can be replaced if we want to here. We can expand that out a little bit. We know that if it's at 180 degrees, it's going to be the negative x component, but friction is equal to mu times Fn. So we might as well plug that in now, so we're ready to go when we need it. And then finally, 270 is straight down, so nothing in the x, and it's all negative y. And now we're ready to go. Remembering that our ultimate unknown is the acceleration. We're interested in figuring out the acceleration. Now, what's in our way? We don't know the normal force. We do know mu. So mu is not a problem. We've got that down. But normal force we don't know. So we can't solve the x column right now. However, fortuitously, the y column does give us information about the normal force. So we can start in the y column and work our way over. So in the y column, Fn minus 294 equals 0 newtons. I'm just pulling everything out that's not a 0, except if it's at the end of the equation. So therefore, normal force equals 294 newtons. Not unexpected when there's nothing else going on in the y direction, but remember, don't assume that the normal force is opposite the weight. Let the equation tell you that. Next up, we have the x equation, 95 newtons minus mu k Fn equals max. And I'm gonna break my tradition a little bit here. Instead of solving this out directly for A, let's tease out the left side a little bit so we can answer the first question. The first question says, is the box accelerating? We'll know if the box is accelerating if the forces are unbalanced. So let's take a look here. We've got the mu is 0.20. The normal force we now know is 294 newtons. And so that's 95 newtons minus 59 newtons. So yes, the object is accelerating. Since the force to the left and force to the right do not balance out, the force to the right wins, so the box will be accelerating to the right. So we can just wrap up from there. 36 newtons is equal to 36 kilograms meters per second squared equals max. So acceleration is equal to 36 kilogram meters per second squared over 30 kilograms. And when we take a quick peek at the units, kilograms cancel with kilograms, leaves us with meters per second squared, so the units work out good. And when you finish with the math, you end up with positive 1.2 meters per second squared. And again, traditionally, you don't have to write the plus, but writing the plus helps you remember to write the negative too when it's time. And there we go. So is the box accelerating? Yes. How much? At 1.2 meters per second squared. Just a quick closing thought to wrap this problem up. One of the things that makes friction challenging is because you're often going to be faced with choosing between static and kinetic friction. And the secret to doing that successfully is to look to see if there's any slippage. If there is slippage, meaning one surface is sliding with respect to the other, then make sure you use the values associated with kinetic friction. If there's no slippage, meaning the surfaces are not moving with respect to each other, then you'll use static friction. And again, this isn't asking whether or not the objects are moving overall. It's asking specifically what the relationship is between the object and the surface that it's on. It's also possible that a problem could switch it through the problem. Part A might be dealing with a static friction scenario, and then the same object might break into motion, and object B might be dealing with a kinetic friction scenario. So watch carefully the information that they give you, and be alert to the idea that it's not a guarantee that it'll be the same thing throughout the entire problem. Okay, if you found this solution to be useful in advancing your understanding of friction and dynamics, please consider liking the video. If you have any questions about the way I solved it out, leave it in the comment field below. And to help the channel grow and find out what's coming next from Transparent Physics, please consider subscribing to the channel. Hey, well, thanks for sticking around to watch that problem get solved out about friction. Hopefully I made things a little clearer for you on this episode of Transparent Physics.